Okay, so I put up a couple of diagrams here that we're going to look at for just a minute, just to look at the different pieces here. So here we have your PCs, okay? And we have them going into a switch. Okay, now who knows the difference between a hub and a switch? Okay, in the past we used to only have hubs. Hubs were basically a way to plug like 3 computers into a device, 3 or 10 or whatever, and then you can connect them from the hub to your router or wherever you're going next. The problem is that with networking you have something called collision domains, which basically means that the data kind of bounces off each other, and you can actually get corrupted data or slow communications by using a hub. So basically what's happened is that we've gone to switches, and basically if you have let's say you have let's say this is a hub right here. We're just looking at those 4 little yellow ports there. If this is a hub, that means all the data that's going into there needs to be shared by that one channel, okay? And there can be slowness or cross confusion when that happens. So what they do with a switch, and you can see in this diagram, if I was able to get that link out of the way, that there's something here called a switch. So what a switch does is it does exactly the same thing that a hub does, except each one of these different things here is like a different lane on the freeway. The traffic stays in its own lane, okay? So any traffic that goes through this lane is going to stay with this lane. That doesn't mean you can't have only one computer on here. If you have 2 computers, they'll both go through this, they'll both be in the same lane. If you have one computer in each of one, they won't ever bump into each other because they're always on their own collision domain and they're not going to interfere with each other. You can have 10 on this one, 10 on that one, 10 on that one, and 10 on that one if you want. You have 40 computers if you really want to have that many, but that's not advised, okay? So we talk about switches basically as each one of these computers, even though they show it all coming into one place, they're all going into their own little receptacle on the switch itself. And they're all traveling from there. They're going from the switch to the router. Okay? Now all of these are on the same network. So if they have a subnet mask of 255.255.255.0, which means they can have a number of computers working, what's your router probably going to have as an IP address? 192.168.0.1, okay? That could be, that's probably the default gateway, your router's IP address. If you want to administer that router from your computer itself, you'd go into the browser, you'd put in http://192.168.0.1. It would bring you up to your router management page. You'd have to put in your username and password, and you can change configuration items from there. Okay, so let's say this is .2, .3, and .4. Okay, and .5, .6, and .7. Okay, so we said this is 192.168.0.1. This is 192.168.0.2. Those are 2 unique addresses. On your network, your mail will get delivered correctly. Okay? When you're using network address translation, remember your router is using a public IP address, and your computers inside your network are using a private IP address, unless you spend a lot of money on IP addresses, which most people don't do. When you send a datagram or packets to the internet, you're going from this computer through your switch forwards it to this router. Your router remembers where it came from on your network, 192.168.0.2, it changes its IP address to something that can communicate on the internet, which is the one that was given by your ISP, and it can go out to the internet, and you can go to a website or whatever, and then when that website comes up, it goes back to your router. Your router knows where that went to because it wrote information in those packets telling it where it's to be directed. And since it knows it's going to go to the .2 device, it's going to come back to the switch and make it back to here. Does that make sense? So when you send something to the router or anywhere on the network, it's going to, if you're sending a message from this computer to this computer here, it's going to note in those packets what the IP address is that it came from. It's going to write them into the packets that are sent within the network and also out to the internet, okay, or another external network. So every one of these devices here has its own address. This Wi-Fi device here is going to communicate with your devices within your network. This would be called an access point. And then the IP address from this device here is going to get translated so you can go out to the internet. And then it's going to come back with the information you requested, and it's going to go to here, and this device knows which device it came from, so it's going to deliver the web page or whatever to this here. So when you send something out to the internet, remember I said we were talking about these packets, okay? Each one of these packets contains something called a payload. It sounds something like you'd hear when you're talking about rockets and airplanes and things like that. It carries a payload, and that payload is information about where it came from, where it's going, and how it's going to get there. And it's pretty much the routers that determine, when you send a payload to the router, it doesn't know how it's going to get to the internet. But this router has something called a routing table, and it knows the best way to get from here to here to your website and then back again. All the routers along the internet have something called a routing table, which have the suggestions to get back to your network or from your network to another network far away. It may need to go through 10 routers to get to your destination and 15 routers to get back to where you started from. Each time it does that, it's called a hop. It takes one hop. How fast does data travel over the internet?
Speed of light.
Speed of light. Yeah, it travels at the speed of light. So however fast the electronics are inside the routers and the efficiency for transferring that information, that's how fast your information is going to be transferred. So even if something has 10 hops, which is actually quite a few hops, it's still going to get to where you want to get to. If I were to do a well, you can actually see the number of hops that it takes to go from one place to another. We won't demonstrate that right now. So, NAT. We've talked about NAT a few times. NAT, network address translation, that is how your internal network can have private IP addresses, because when it gets to your router firewall, that's where your NAT translation takes place. That's where the internal network packets are stripped off and sent out to the internet with the IP address and location of this router right here, because this has a real public IP address. So it can get out to the internet, and it can get back here because this is a known IP address on the internet. It's in someone's router table or close by. It's in your ISP's router table, so it knows how to find you. And then your computer knows, your router, which is a computer, knows how to translate back to an internal network address, which is using network address translation, and you can get back to the node that it started with. So it's a little bit complicated how it all works, but basically it's just a heck of a lot of bookkeeping. And that bookkeeping doesn't need to be done by you. It's done by your networking devices. Now, and then we have something else called PAT, and she's sitting in the room right next to me. That's port address translation, and that takes NAT one step further, and that, let me click on that, might give us a better understanding. Port address translation is an extension of network address translation that permits multiple devices on a LAN to be mapped to a single public IP address to conserve IP addresses. So that's kind of what we were talking about. But what PAT does, it's an extension of that. On your computer, you have, in TCP/IP protocol, you have these things called ports. Okay, and ports are like, you walk into your post office and you have all these post office boxes. Okay, well, walking into your post office is like walking into your network address translation table. And each one of those little mailboxes could be another little single port that's attached to each one of those addresses. So you can actually expand out your number of addresses, hundreds of thousands more if you need to. But in the environments that we use, we usually don't go the direction of PAT because we don't have to, because the network address translation is enough. Okay? So, what's a server? Okay? A server is usually where you keep your data, where you do your printing from. Most of us will print from our own PCs and things like that, but in a larger network, and this one has 6 devices in it, actually 7 here, because it has a workstation. A little USB stick, that can be considered a server. If you plug a little USB stick into one of these little USB ports, now when I'm talking about a USB port, I'm not talking about the same kind of port I'm talking about with TCP/IP. It's a different kind of port. This port is where a TCP/IP, this is where a USB type A connector goes. This is where its home is, right there. That's that kind of port, like a ship coming in the port. It knows to go to that one. It's the only place it fits. But that can also be a place where you store files and things like that. So that can be a server. This is a little bit overkill for what we usually have in our home environment. But here at the Shipley Center, they do have servers as well as peripheral PCs. And we're connecting using iPads and iPods and things like that to that network. But basically, the whole point of this whole thing here is that all your devices in your internal network have to go through a router, and then they have to go through some kind of device to get it out to the internet. And for this modem, it's probably back to the days of the telephone modems, but at the same time, it could be a cable modem like you'd get, with Wave or with or Olipin, or it could be something called a DSLAM, which you would get when you're using a network that's using DSL networks. But basically, it's just a way of getting you outside your network to the internet and then back into your internet. Most of us only really care about all this stuff that's in here, our computer at home. We don't really need to worry about what goes on beyond the router, unless of course you can't get to where you want to go. And then you call the ISP, or you go online and see if they're up or down. And if you call the ISP, they'll tell you they're up, even though they may be down. But if you actually go out to some websites, there are websites for like Nicola and CenturyLink and Wave and things like that, where you can see where their outages are. And so if you go to the Wave outages, it'll actually show you bubbles where the current outages are. And there's always outages somewhere. But most of our traffic for the peninsula comes through Seattle. So if Seattle's out, we're usually out as well. Although our actual cabling comes from Bonneville, and that's where we get our high-speed internet. And we're so lucky out here on the peninsula, being kind of a small community, having as fast internet access out here, if you're lucky enough to live near one of the ISPs or have the type of connectivity, that you can get some really high speeds out here in Sequim. Or else you can get crappy service too, if you have if you live too far away from the main line or something. So it's kind of a big deal when you're buying a house and you want good internet access, you have to find that out first before you make your purchase, because you may not be able to live there if your job depends on it, getting to the internet and working. So some of these networks are quite large and bulky and things like that. We can be looking at all kinds of things. We have companies like Cisco. You know, when I first got into the networking world, I never even heard of Cisco. I thought he was the guy who did the weather on the TV. But Cisco is a huge networking company, and they specialize in routers and firewalls and switches and things like that. You'll find out that if you work in industry that a lot of companies will only buy Cisco equipment. It's expensive, but they stand by it, and they have good engineers to help you out if you need it. So that's why they have such good penetration into the market. This is what a rack looks like in a data center. Has anyone ever been in a data center where they've seen the big racks of servers and switches and things like that? It's really quite amazing. I can't tell you the flutter I had in my heart the first time I walked into my first job after working on 1 or 2 PCs at home and walking into this room that had all these servers in a rack and all these lights flashing and all these cables. You know, I thought I died and got into heaven. You know, it was one of those things. But after a while, I kind of settled in and realized it was just a job, just like anything else. But data centers have hundreds and sometimes thousands of racks that have servers and networking devices and things in them, and it's really quite exciting to see it all for the first time. But they're large air-conditioned buildings, you know, that they have diesel backups in case the power goes out, so that their machines keep on running and things like that. They're constantly having tests to make sure they can recover in case there's an emergency outage or something like that. A lot of companies on the west side of the Cascades, they have their data centers and the backup data centers over, like you know where Liberty Lake is, over by Coeur d'Alene, but on this side of the Spokane side of the border here. A lot of them are out there because they're not in the same earthquake zone as we're in. So if we have an earthquake out here that wipes out everything, they can still route all their traffic through Liberty Lake data centers and other data centers in that area. And a lot of eastern Washington, there's a lot of little farming towns that now have giant data centers in them. Where else do you find like Amazon data centers and things like that? Along the Columbia River, because they're wonderful sources of hydroelectric energy. And these things use a lot of power. These data centers use a lot of power. So they want to go places where the power is cheap and readily available, okay, and reliable. So this is kind of like what stuff in a rack looks like. As you can see, some of the networks get quite detailed. Here you have networks that have 192 addresses connected through routers that connect to 209 addresses that connect to networks that have 10 networks on them. And remember, the routers know how to handle different networks. They have routing tables and they know how to move from one network to another network. So if you have, where is that routing done? Well, first the information has to come in through a network card, just like you have in your computer. And then it's taken into the internals, it's looked at, it's inspected, and it's moved into down the right path so it can communicate and get you to the internet and back from the internet back to your own device. I know that's kind of a lot done really quickly. This is a view of switches. This is a desktop switch. You may see a desktop switch where you have multiple computers. I think there's one in the, well, this is basically a switch right here. Okay, and then you have internal network switches. So this is, I can't count the ports here, 2, 4, 6, 8, 10, 12. This is probably an 18-port switch. You can have 36-port switches or 48-port switches. Switch works on layer 2 of the network. Remember what layer 2 is? That's the data. Let's go back to our picture, data link layer. Let's see. So a switch works on the data link layer. Does it need to know your IP address? No, it doesn't need to know your IP address, because the IP addresses don't come into play until you get up to the network layer. When you're talking, we want devices to communicate directly over the network and talk to each other individually. You need to talk through the network layer. The data link layer just gives you a pathway to get somewhere. Okay, it will just get you there quickly, a lot quicker than something that works on the network layer, because the network protocols are quite a bit more complicated. But you can have something called a layer 3 switch. Okay, so what do you think a layer 3 switch does? It does switching and what else? Networking. Okay, that means not only can a layer 3 switch just transfer stuff at the most basic level, it can use networking IP addresses to route information through your network. So it's a lot more accurate, and it's a lot more, you can make it a lot more secure and a lot more versatile by using a layer 3 switch. Now that's not something that any of us would use in our homes, so you don't worry about it. Any switch that you buy is going to be a layer 2 switch, okay? Unless you bought one used on eBay or something and want to learn how to configure it. So, I don't know what this is. It's a Thrangy Cat security flaw uncovered by Cisco routers. I thought it was kind of a cool picture. That one's not politically correct. I'll get up with that right away. Okay, so RFCs, we talked briefly about this before. An RFC is a request for comment, okay? Like I told you before, one of the coolest things about working with computers and network devices and things like that is that there's a lot of logic to it, okay? And you can trace that logic back to a lot of really smart people who've discussed these and decided on what the standards are, and if you stick with those standards, you can usually figure out what's going on. It's not an ad hoc world where everything is, you just guess everything. And one of the reasons I like computers, because they appeal to my logical understanding of things, sort of like algebra. You know, you can count on getting the same answer if you follow the rules of algebra, if you do over and over again. Although there are some exceptions. Not real exceptions, but there are people who make things look like exceptions. Okay. TCP as a transport layer, IP as a networking layer are how we communicate mostly on the internet. The protocols that you're probably more familiar with are, we talked about DNS and DHCP today. DHCP is how you assign your networks, default gateways, and things like that to your computers on your network automatically. DNS is how you translate your addresses on the internet. FTP is file transfer protocol, how you can transfer files and things like that over the internet or in the internal network. HTTP is how we look at the internet through the HTTP protocol, hypertext transfer protocol, and it's for looking at the World Wide Web and other clicking on links and things like that, hypertext documents. HTTPS is a more secure version of that protocol. IMAP is for, remember that's for mail. LDAP, that's a lightweight directory access protocol. Now, what do you think lightweight means? It's like simple. Simple is supposed to be simple, but it's really difficult. Lightweight basically means it's really heavyweight, but not as heavyweight as the real thing. Okay? So when you see the word lightweight, you know, it's not really easy to use. So there are a whole bunch of these different protocols, and I'm not going to bore you with going through all of them because it's not necessary. That's not why you're here. But the main thing is you have to know that things go up and down, you know, from your computer interface. They have to get to the wire somehow. They have to get to another computer somehow. have to go up and someone else needs to see it or something else needs to see it, then it needs to get back to your computer. Otherwise, what's the purpose? Okay, so we're going to talk a little bit about Windows networks for just a couple minutes, and there are basically two kinds of Windows networks. So if you have two computers in your house and you want to share information between those two computers, okay, and those two computers are already connected to the internet, what kind of protocols do they already have on them? TCP/IP, right? Now when you have a group of protocols put together, they call it a stack, okay? So you'll hear the term TCP/IP stack, okay? And the TCP/IP stack was like what we looked at in that last screen that had like FTP and DNS and DHCP and things like that. Those are all the protocols that are included in the TCP/IP stack, plus the different layers that it has to travel and travel up. So those are already set up on your computer if you're already talking on the internet. So why not use TCP/IP for your internal networking? Well, it's slower than NetBIOS or NetBEUI, okay? Well, that's true. So back in Windows 95 and Windows 3.1, most of our internal networks in an office were not connected to the internet back in the early 1980s. They were just, one person at one desk wanted to share a file with someone else in the same office. So they would use the Microsoft protocols, which were really quick, but you couldn't communicate over a wide area network, just over a local area network. And then Novell came along with IPS-SPX, which actually did have a little bit more routing abilities to it. So when the Novell networks, and we remember Novell networks, if you haven't worked with them, you may have at least heard the word. They kind of were the most popular networks in the late 1980s until TCP/IP came over. And why did TCP/IP get so popular? Because it can be used on any kind of a system. It can be used on a router, a computer, a switch. It can be used on a Linux network or a Unix network or a mainframe computer or a PC computer or anything. So it was a real versatile type of computer. That's why the TCP/IP stack is so popular for doing networking these days, because what it lacks in speed, it makes up for in reliability and versatility. Okay, so that's why we're using the TCP/IP stack. But with peer-to-peer networking, and I believe I have a link here. Search for Google, can I find it? Ready, set, maybe not. Oh, here we go. So, it's peer-to-peer networking, okay? Sometimes P2P also means point-to-point, but that's for another day, another story. But a peer-to-peer network interconnects nodes, peers, that share resources amongst each other without the use of a centralized administrative system. So with a peer-to-peer network, you don't need a server. Okay, you don't need a server for your permissions, you don't need a server to define your shares, but you also don't get all the security that's associated with that as well. What they're not showing here is you can also have a printer on a peer-to-peer network, so all these nodes can share a single printer if you want. Or you can have multiple printers that could be actually connected directly to the network or connected to each device themselves, and they can be shared with most different protocols. So a peer-to-peer network is basically a small network with very few rules and a lot of flexibility. Okay, so you'll find a lot of small offices will have peer-to-peer networks and share resources. Okay, and that's usually what is called a LAN or local area network, and they're not real complicated, although Microsoft sure did find a way to screw them up with their home groups and other updates and things like that. And I didn't become a Microsoft certified guy because I thought their systems worked so well, it's because I was fixing them all the time. So, you know, but that's true with pretty much any technical type of job. Nothing ever works like it's supposed to all the time. So we can talk about more about peer-to-peer networking, especially if you want to set one up at home. They're fairly easy to set up. Microsoft went to something called the Home Group, which a lot of people came out. I think it came out with Windows 7, I believe, or maybe a little earlier with XP. But they got rid of it. They don't use the Home Group anymore because it actually brought more problems. In other words, but anyway. Every computer has a network name. Like yours might be called Sherry's computer, for example. Mine might be called Bruce's computer, and that's how we see each other on the network. Okay, and each one of our computers might have files that I want to share with you, and you want to share with me. Or we may have one computer that holds on to all the files that we all want to share, or it can be distributed amongst different computers. But it's not necessarily centralized. Doesn't have to be centralized. The next big thing is, hopefully this won't take too long to come up. So, a Windows domain, okay? Now a domain is a special kind of network. A domain has a server, or it could be a PC, but it's a computer that acts as a computer that serves the whole network, and it keeps track of all the usernames and all the passwords and things like that. So when you are on a Windows domain, which has all the user accounts, computers, printers, and other security principles are registered with a central database, it's known as a domain controller. And usually domain controllers are a fairly powerful server type machine, which means that they serve the other nodes on the network. But they also, like I said, they keep track of usernames and passwords and things like that. And usually there's security on those. The basic security on those is the password for those type of domains. So password level security is the most basic thing you're going to see on these networks. Now, other things that we're seeing in the modern times is we're seeing encryption, you know, different types of securing your data as well. But that really doesn't have a lot to do with the Windows domain. So your computers can connect to a domain via a LAN. A LAN is a local area network. It's also a TLA, a WAN, a wide area network, or a VPN connection. VPN stands for a virtual private network, okay? And a virtual private network is usually a server that will allow you entrance into another domain or another place on the network, but it's done in a private manner, okay? And we're not going to talk a whole lot more about those right now. But in a Windows domain, we have something called the domain controller. And the domain controller controls all access. It controls access to files and printers and computers and things like that. Most of your big corporations that are running large Windows computer networks are running Windows domains. And that's a whole subject in itself that can go on for days and weeks and months, and we're not going to go there. So I hope in this session that we covered some stuff that may be new to you. Hopefully, when you get your network set up at home, you do have a firewall. What does a firewall do?
Security.
It controls traffic in and out of your network. It says, well, where can people get to, and who are the people who can get there, and when can they get there, And what protocols can they use, which ones can they not use? When you have a Windows 10 computer, do you have a firewall built into it? Yeah, you do. If you have a router from one of the major companies, does it have a firewall built into it? Well, most of them do. Does your ISP have firewalls? Yeah, they do. So there's lots of different layers that you can go through and get firewalls and control the way information passes through. They usually use things called access lists that can be used for either controlling what traffic can go through a firewall or from what resources you're able to get to because you're either on or not on that access list. So with that, I think I will wrap it up at this point. And are there any questions that anyone has off the top of their head right now? Yes.
One thing that occurs to me is that your network routing, in today's household, it should include a lot of devices, like refrigerators, garage door openers, the heating systems.
And it can.
All of those are networks that, at least the house I bought, have the capability of being on the network.
Mm-hmm.
And I choose not to put them on there because
Right.
I don't want to let anybody else have access to them.
So those different things are called the Internet of Things, you know, and they can be devices like light switches and refrigerators or whatever, and you can make it as complicated as you want, and I can guarantee it won't work all the time, but you'll sure have fun trying to get it working.
One thing that discouraged me was the garage doors openers. You put them on there and then you can tell if the door's open and when it closes and all that, but mine kept opening at strange times. Like
Did it really?
1 o'clock in the morning and 3 o'clock in the morning.
Uh-huh.
When I called the lift master, they said, delete it. I did. But all of those devices would act as things on that chart for you in your house today. And there are probably more coming.
Okay.
Yeah, I mean, you just have to be careful, you know, there's a lot to know, and as you can see, there are people out there who know a heck of a lot more than we do that can take advantage of us if you do too much of that stuff, so you just have to be a reasonable person when you do that kind of work. Anything else? Well, thanks for coming tonight. I haven't really decided exactly what we're going to do next time. Does anyone have any suggestions like they'd like to see? Otherwise, I'll come up with something special.